Dear friends, dear viewers, dear internet, have you ever thought about your weight on the Earth or on the moon? You have heard that you feel lighter on the moon and Mars than you feel on the Earth, and that's of course correct. But already on the Earth, you would feel that you're a little bit lighter if you were in certain places than you are at home, perhaps, unless you're already in the place on the Earth where the Earth's gravity is weakest, and I'm gonna elaborate on that pretty soon. So this is basically a model of our Earth. It's very spherical here, but as a matter of fact, the Earth is oblate, meaning that the radius of the Earth on the equator is longer than the radius pointing to the north and the south poles. So what does this imply? It implies that all the things that you have heard, if you have heard that from school, that G equals 9.8 meter per second square, a constant, use that all the time, or 9.82 if you are in Sweden, and 9.78 if you are in like Thailand, or 79 in certain countries. It's wrong, because G varies. G is never constant. That's one G though, that is a constant, is a capital G, which I'm gonna talk about also in a little bit. So we're gonna touch upon Earth's gravity and its anomalies, and why that is the case. It is the case because the Earth is not spherical and not perfect, and if you want to do a simple analysis, very simple, by throwing away the rotation of the Earth, the obliqueness of the Earth itself, and keep it as a sphere, still you are faced with the problem of where you are on the Earth. So let's say that you are using radius of the Earth, the average value, which is 6,753 kilometers, and you want to compute G at the surface of the Earth, and then we will have only one value for the whole Earth, of course. The thing that will change is the altitude where you actually located. So we have to start off with the fact that you're standing on the Earth and you feel the force that keeps you on the Earth. So basically that's the pull of gravity, and it's because you and the Earth are two different objects, and then we write it down this way: F equals ma, which is basically Newton's second law, and you can write this as m times g, which is basically acceleration due to gravity, which is the thing that we mentioned and we started off with, and we equate them, and then you will see that with very simple math you will come to G equal capital G times capital M divided by r squared, and G here is a universal gravitational constant. It's the same throughout the universe, and that has been discovered or measured for quite a while ago, and the unit that we will use here will be in meters, of course, but you know what to do. Just convert that and throw it in the equation and calculate. So basically we can call it G naught. So that's basically G at the surface. But since you can be flying a plane at 10 kilometers altitude, or you can be in the InSight International Space Station, which is circling the Earth at 400 kilometers altitude, and I would have to point out that actually astronauts flying or on board the ISS at 400 kilometers, basically in space, are not weightless, but they are feeling the so-called apparent weightlessness, and they themselves call this environment they are in as microgravity. So I think we should stick to that, microgravity, and the reason why it's like that is the slight gravity, not so much. You can approximate it at being completely zero gravity too, but it is due to the fact that they are circling the Earth at a very high speed, and that speed is orbital speed, which will cancel out the gravity pull if we ever have to touch upon centripetal force, which I'm not gonna do in this video. But at that speed, basically, you will not feel the pull of the Earth, okay? And if you would fly very fast, much further than that, you will probably leave the Earth orbit and probably go to the moon or any other celestial bodies that we will have to discuss at another time. So doing this and rename it as G naught, you actually can think of the altitude as being Z and add it right here. So it will be the radius of the Earth up to the surface plus Z squared everything, and use a math to actually rewrite that, and you will see that G divided by G naught, which is basically that, will be this expression. And then you can plot G divided by G naught. What you end up having is a plot that looks like that. So what we come to as a conclusion is that at about 300 kilometers, you lose about 10%. And when you go up to about 1,000 kilometers, which is of course an outer space, there's no atmosphere right there, you lose 25%. So if you can build a structure 300 kilometers tall, at the top of it, if you can bring up your scale and stand on that scale, you will feel that you will lose 10% of your weight that you feel on the surface of the earth. And if you can build something that is 1,000 kilometers and take away all the rotation and simplify everything, you will lose 25% of your weight. Your mass remains basically the same unless you spit out something. But let's not discuss that. Let's simplify it. So still, that's the case. Depending on the altitude that you are located at relative to the Earth, that is how G varies. But as a matter of fact, you have to take into account the mass anomalies of the Earth as a celestial body, and also its rotation and its obliqueness and everything. But we will come to about 9.807, which is actually a standard thing if you use this value. And then in different countries, you are taught with different numbers. But still, G, or acceleration to the gravity, is never constant. And in 2002, NASA, in collaboration with a space organization in Germany, launched a project called GRACE to study gravity anomalies of the Earth. And I will walk you through that on my computer. So if you have any question, wait until that, and then we'll see what we come to a conclusion. Okay, so it's going to be exciting, and you will see that on top of the Himalayas and on the sea level, you have two different gravity field strength, or basically two different G values. Let's watch what I have to show you on the computer screen. Right here is the website for the GRACE project, and you can go in, type in grace.jpl.nasa.gov, and GRACE actually means Gravity Recovery and Climate Experiment. So what you're seeing, which is spinning really fast right now, is a model, very highly advanced model that the GRACE project, basically two satellites sent up into orbit with the help of laser technology that measure anomalies of the Earth's gravity, came up with. And you can see blue means weak and red means strong. So since it's spinning very fast, I don't want to pinpoint where, but you can see oceans and mountains and all that, like the Himalayas. I probably can catch that, yeah, right there. So it's strong gravity, and despite the fact it is like higher altitude, but there's a lot of mass concentration. And notice where you have a mass concentration, then it's stronger gravity and all that. So if you want to launch rocket, you probably want to avoid the area where you have very strong G, but still you can compensate with more fuel and maybe better flying technique, launch technique whatsoever. But I hope you're convinced now after this multi-million space project by NASA together with German space agency, that G is never constant, never ever anywhere on the planet Earth, and not anywhere on asteroid or the moon or the Mars or any other planets. And you actually can use simple mathematics to compute anyway ideal G on any planet or any celestial body. So yeah, that's it from me for now. Hope you have enjoyed this video, and if you like it, just give me a like and subscribe if you haven't. Alright, until next time, have a good day or good night.